Hello, Mr. Betts here. I want to take a look at a few more examples, whether or not we can use the integral test for convergence or divergence. And so keep in mind that for the integral test to work, the function that models the sum or the terms in the sum have to the terms have to be approaching zero. That's the nth term test for divergence. But then also for the integral test, the terms have to be decreasing and positive. Well, if n is increasing, these terms are all going to be positive here. However, if we look at what happens as n gets bigger for these terms, the looking at the relative rates of growth or dominance of the functions, the numerator being a polynomial, since that's n to the 1/2, and the denominator being a log, the numerator is actually going to be growing faster than the denominator. So this limit itself diverges, which means that the nth term test for divergence tells us that this diverges. So we don't even need to use the integral test here because the terms are not approaching zero. So we'll say this diverges by the nth term test for divergence. So pretty straightforward example to start with here. But the point of this example is to remember that we can always use the nth term test for divergence first to see if the series could possibly converge or not. This one cannot possibly converge because the terms themselves do not approach zero. Now, in this example, as n gets bigger, the terms do approach zero. So this is a candidate for the integral test. So the first part of the question says determine if the integral test applies to the series. And since the terms, as n gets bigger, since the terms themselves are going to get smaller because e to a big negative power is going to be close to zero, those terms are going to be decreasing. So e to any power is positive, but e to a bigger negative power is going to be closer to zero than e to a smaller negative power. So the terms are positive and getting closer to zero, so the integral test applies. So the function that we're going to be looking at here is going to be e to the negative x. And so what we want to look at then is whether the integral from 1 to infinity of e to the negative x converges or diverges. This is an improper integral, so we are going to rewrite this as a limit. So we're going to look at the limit as c approaches infinity of 1, the integral from 1 to c of e to the negative x dx. The antiderivative of e to the negative x is going to be negative e to the negative x, and we're evaluating that, let's use brackets here, from 1 to c. So that's going to be the limit as c approaches infinity of negative e to the negative c minus negative e to the negative 1. Well, as c approaches infinity, e to the negative c is going to get closer and closer and closer to zero. So this term here is approaching zero, and so this sum here is approaching 1 over e. And the sum itself doesn't matter. What matters is that this is a finite integral. So the integral itself converges, and the integral test says that the integral and the sum will either both converge or diverge. So the sum itself will also converge. And that's it. One final example here. This example is a little bit more challenging. I do want to point out that as n gets bigger, the denominator is getting bigger, so the terms are approaching zero. Also, as n gets bigger, the terms are all going to be positive, so it does meet all the criteria for the integral test. So the function that we're going to be looking at is going to be 1 over x times the square root of the natural log of x. So we're going to be specifically looking at the integral from 2 to infinity. Notice I started at 2 because n starts at 2 here, of 1 over x square root of the natural log of x with respect to x. So we're going to rewrite that as a limit because it is an improper integral. And this integral we're going to evaluate using substitution. So in its current form, we cannot evaluate this. However, if we let u equals a natural log of x, that's going to allow us to substitute u for the inside of that square root. And also du is 1 over x dx, which is going to allow us to take care of this x here. Now I'll go ahead and solve for dx here. So dx is going to be x times du. So we're going to substitute x times du for the dx here. Also, when we make the substitution, we need to remember to substitute our limits. So making all of those changes here, we're looking at the limit as c approaches infinity of the integral. We are changing to du, so the 2 for x is going to become the natural log of 2 for u. The c for x is going to become the natural log of c. And our integrand here is going to become 1 over x square root of u. And then dx is going to be x times du. So the x's cancel each other out. I'm going to rewrite our integrand as u to the negative 1/2. And we can evaluate that. So this is going to be the limit as c approaches infinity. U to the negative 1/2. The antiderivative is going to be u to the positive 1/2. And then we're going to divide by 1/2. So it's going to be times 2. So it's going to be 2 square root of u evaluated from the natural log of 2 to the natural log of c. So evaluating that, we're going to have the limit as c approaches infinity of 2 square root of the natural log of c minus 2 square root of the natural log of 2. So 2 square root of natural log of 2, this right here is just a constant. However, this part right here, as c approaches infinity, the natural log of c is also approaching infinity, which means that the square root of a number approaching infinity is also going to approach infinity. So this does end up being an infinite sum. So this limit is going to diverge, which means that the integral diverges, which means that the sum that the integral corresponds to also diverges. Now, I do want to point out that this series is going to be a very slowly growing series. We've looked at the harmonic series before, and the harmonic series is a very slowly growing series, but it does diverge. It adds up to as big a number as we want. This one is going to grow even slower, but it is still going to grow fast enough that it's going to add up to any sum that we want. So no matter what we pick, we can add enough terms to get to a sum greater than that number, so it is a divergent series.